Toward the end of the last lecture, we did something that wasn't even asked for. We generated a system curve. Well, now let's start talking about that in more detail. I showed you a spreadsheet, and for that previous problem, the valve was in the fully open or 100% open position, and that brings up an important point. When you generate what's called a system curve, you do that for a given position of the valve. And in the last lecture, we happened to do it for a fully open valve, but it could be partly closed. What is the system curve? It's a graph which has, on the horizontal axis, the volumetric flow rate Q through whatever piping system we're talking about. For us, it was a pipe that went from the whole tank to the liquid extractor, and it had elbows. And what is the vertical axis? On the vertical axis is the total head required to maintain that flow rate. Now, when you talk about total head, that's really the work that you have to do on the fluid. Specifically, it's the work that you have to do on the fluid per volume divided by rho g. So, going back to the previous lecture, this is the formula that you use to calculate the work that you have to do per volume of fluid, and all the terms are there that we talked about. You have to do work to pressurize the fluid if P2 minus P1 is bigger than 0. You have to do work on the fluid to lift it, to elevate it, if Z2 is bigger than Z1. I've crossed out here these terms involving U2 squared and U1 squared. Again, they're there in principle. Usually you have a pipe of a constant diameter, so you do not have to do work to accelerate the fluid or increase its kinetic energy. And of course, the other big ticket item here is you have to overcome friction. So this is, going back to the previous lecture, the work per volume that you're doing on the fluid. And the head is nothing other than that, just expressed as an equivalent height of liquid. So you just take that and divide it by rho g. So the system curve really is a plot of how much work you have to do on the fluid to push it through whatever the pipe system is at a given flow rate. I showed you a spreadsheet like this in the previous lecture. I've just modified it a little bit. This is too small to see, so let me just blow it up a bit. What I've done here is put myself some reminders here of what the K values are for different positions of the valve. K is 9 for the fully open valve. K is 36 for the half open valve. K is 112 for the quarter open valve. Clearly, the more choked off or closed the valve is, the more friction there is. This is really huge. You know, a valve which is only a quarter open has this huge coefficient K here. And I've put that number in the cell here so that I can easily change it. Notice that by far the biggest contribution to the friction in our pipe system is the valve. So, in the previous lecture I showed you just the table from the spreadsheet. Well, here's the graph that goes along with it. For the fully open valve, this was the relationship between head, or work that you have to do on the fluid, to push it through the piping system as a function of the flow rate. Clearly, the higher the flow rate, the more work you have to do on it. So you get a curve like this. Notice, by the way, that this 3 feet, that's the static part. You have to lift the fluid 3 feet, and that really isn't dependent on velocity or flow rate, but clearly the head goes up. You have to do more work per volume of fluid the faster you push it through the pipe. So you get a curve like this. Now I'm just going to toggle between this graph and some other graphs. So what if you close off the valve more? 100% open, 75% open. Notice that the curve goes up. So at a given flow rate, for example, at 100 meters cubed per hour, here the total head I need is a little bit under 5. It's gone up. Now it looks like about 5.4. So the curve gets higher. You have to do more work to push the fluid through the network if the valve is more choked off. What happens if you close off the valve even more? Curve gets even higher. Close it off even more. Curve gets even higher. This progression of curves, these are each a system curve for different values of the valve position. 100% open, you have to do a certain amount of work at a given flow rate. You just have to do more work when the valve is more closed. More work, more work. So that's really the message here. The more choked off the floor, that means the more work you have to do per time or per volume of fluid to maintain a given flow rate, expressed as a total head H. This is a characterization of our piping system. That's information that exists just independently. Of course, we actually want to push fluid through our piping system, so what's going to do the work for us? The pump. is going to do the work for us. And so that's what we're going to talk about next.